Welcome back. So we're talking about linear differential equations with forcing. So instead of just a homogeneous differential equation, which is what we've mainly been talking about up until now, lots of times our system, our differential equation system of interest, is being actively forced by some external disturbance or by some control input. So for example, we derive the equations of motion for a mass on a spring attached to some rigid wall or some rigid mounting, and we have derived the equations of that kind of isolated mass on a spring. What if I put an external force on the base? I move the base up and down at some rate, or I do something like that. That would constitute an external forcing or an external control or disturbance, and that would give rise to an inhomogeneous differential equation with this forcing term. So huge amount of applications. For every unforced differential equation, there are infinitely many ways you could force it. And so this really opens the doors to things like control theory and solving for a broader class of dynamics. In the last lecture, I showed you how to solve this inhomogeneous equation with the method of undetermined coefficients, which is pretty easy, but also a little bit limited. Now I'll show you method 2, the variation of parameters. It's a little bit messier, a little bit trickier, but it will be much more generally applicable to a wider range of forced differential equations. This f of t does not have to be one of those linear building blocks, an exponential function or a sine or a cosine. It could be kind of any nasty function you can write down, and you can use the variation of parameters. In fact, the coefficients out front of these terms could be polynomials of x themselves, or functions of x, and you could still solve this using variation of parameters. So I'm going to jump in. I'm going to use this simple example just because it's easy to make everything work in this example, but you could do this for a more general f of t if you like. Okay, good. So the idea of the variation of parameters is basically to take your homogeneous solution. So if we go down here, the solution to our unforced homogeneous equation is just a sum of two exponential functions, where the -1 and -2 here are the solutions of our characteristic polynomial. Okay, so these are the two fundamental solutions that solve this differential equation, and so any linear combination is also going to be a fundamental solution, is also going to be a solution. And so what the method of variation of parameters does is it replaces these constants with functions u of t, u1 of t and u2 of t. And so what we're going to do is we're going to say x of t is equal to, instead of these constants, we're going to say it's u1 of t e to the minus t plus u2 of t e to the minus 2t. And we're going to plug this into our differential equation in blue here, and we're going to solve for those functions u1 and u2 of t that satisfy this inhomogeneous forced equation. So there's a lot of degrees of freedom here. These are arbitrary functions u1 and u2. They can be anything at all. And so we'll hopefully get some conditions on these that allow us to satisfy this equation. Okay, so as always, what we're going to do is compute a first derivative and a second derivative, and then plug that into this equation and try to see what cancels. Okay, so x dot is pretty simple, x dot, but because u is a function of t and e to the minus t is a function of t, we're going to have to use the chain rule here. And so we're going to get that this is minus u1, I'm going to drop of t, just assume it's a function of t. It's minus u1 e to the minus t, and we're going to write it over here, plus u1 dot e to the minus t. So these are the two terms that happen when I take the derivative of this. I get the first term times the derivative of the second, which is minus e to the minus t. So this is minus u1 e to the minus t, plus the derivative of the first term times the second term. That's plus u1 dot e to the minus t. And I'm going to do the same thing for this term here. So that's plus the derivative plus u2 times the derivative of the second term is minus 2 u2 e to the minus 2t, plus the derivative of the first term times the second term is u2 dot e to the minus 2t. Notice that I basically, using the chain rule, I got these two terms, and using the chain rule for this, I got these two terms, and I split them so all of the u dots are over here. Now again, we have a lot of degrees of freedom in choosing u1 and u2. They are completely our invention and our artifice to solve this equation. So we can plug in anything we like for this u1 and u2 as long as it does the job of satisfying this equation. And to make my life easier in the next step, what I'm going to do is I'm going to say, I want my u1 and u2 to satisfy that this adds up to equal 0. Now at this point, you should be saying to yourself, well, how on earth do you know that you can satisfy, that you can find a u1 and a u2 that not only solve this equation, but also have this condition here? And my answer is you don't know yet, but take my word for it. This will work out. So this is an assumption or an ansatz. We're going to choose a u1 and u2 so that this is true. But it's still, there's a lot of u1 and u2 that satisfy this. And so we're going to then still have degrees of freedom to let them solve this equation. Okay, so we're going to assume that this is true. And generally speaking, in variation of parameters, this is a good assumption, and this will help us down the road. At the end of the video, if you're still confused, you should come back to this assumption and really puzzle with yourself. Did we violate this with any of the further steps that are about to come? Is this going to be true for any forcing? Like maybe instead of writing down a specific forcing, write down a generic forcing and see if you can work out, does this work for an arbitrary f of t, or are there cases where this is not going to work? Okay, but for now, this is a fair assumption. And then we're going to take the double derivative of this again, so x double dot. And using the same basic chain rule, I'm going to get something like, again, u1 e to the minus t plus 4 u2 e to the minus 2t minus u1 dot e to the minus t minus 2u2 dot e to the minus 2t. Okay, no big deal, that's fine. And I'm not going to make that same kind of assumption on this term. I'm going to let all of these terms stay. And I'm going to group this, I could group this if I wanted, into something like u1 minus u1 dot e to the minus t plus 4u2 minus 2u2 dot e to the minus 2t. Okay, so that is my x of t, my x dot of t, and my x double dot of t, assuming that I've relaxed these being constants into being arbitrary functions, or almost arbitrary. I want this to be true. And now I'm going to take these three equations, and I'm going to plug them into my inhomogeneous forced equation, set that all equal to whatever f of t is, and I'm going to solve for conditions on u1 and u2 that have to be satisfied for this blue equation to be satisfied. Okay, so that's what we're going to do now. So now we're going to solve this equation with those x's. So I'm just going to do it. So we're going to say, like what is x double dot plus 3x dot plus 2x, specifically using these expressions here. And I'm actually going to group all of my e to the minus t and e to the minus 2t terms. So I'm going to write this as a big thing, e to the minus t plus another big thing, e to the minus 2t. That's going to equal, okay, so x double dot is this one. So that's a u1 minus u1 dot. Oh, God, this is going to be a mess. Okay, I'm not going to skip steps. This will be a disaster if I try to skip steps here. Let's just plug it all in and then collect terms. Okay. Okay, so this is going to be x double dot is all of this stuff. So it is u1 e to the minus t minus u1 dot e to the minus t plus 4 u2 e to the minus 2t minus 2 u2 dot e to the minus 2t, that's my x double dot term, plus 3 x dot, so that's plus 3 times this stuff, which is a minus 3, okay, because plus 3 of a negative number is minus 3, so minus 3 u1 e to the minus t, minus 6 u2 e to the minus 2t, that's this term here, plus 0 because I made this assumption. Okay, that's my x double dot plus 3 x dot plus 2x, so that's plus 2 u1 e to the minus t plus 2 u2 e to the minus 2t. And of course we know that all of this stuff equals our forcing e to the minus 3t. Maybe I'll just keep that in blue at least for the moment. You know, equals e to the minus 3t. Good. And so now I'm going to rearrange and group this stuff, and I'm going to basically keep, what am I going to keep? I'm going to keep all of my dots separate, and I'm going to keep everything that's multiplying well, you'll see. Let's see. So let's, this equals, I'm going to collect all of my e to the minus t terms, e to the minus t times u1 minus 3u1 plus 2u1. That's all of my e to the minus t's, plus my e to the minus 2t's. That's going to be 4u2 minus 6u2 plus 2u2. And then I also have these dots, these u1 dot and u2 dot. So minus, this is minus u1 dot e to the minus t minus 2u2 dot e to the minus 2t. All of that equals e to the minus 3t. So I've just rearranged and collected all of my terms by plugging this stuff into this equation. You can tell this is a little messy, okay? But here's what gets really cool. All of these coefficients add up to 0. u1 minus 3 plus 2 is 0. So this adds up to 0. 4 minus 6 plus 2 also adds up to equal 0. And specifically, these add up to equal 0, like, because e to the minus t and e to the minus 2t were solutions of my homogeneous equation. So essentially these are just, you know, an outfall of the fact that I started with a solution of my pink equation. So these add up to 0. You can convince yourself that that's kind of always going to be true. And now I have this very simple differential equation here. Essentially I can ignore everything here. And this is the differential equation that we now have to solve. Okay, so now this is the only equation for u1 and u2 that I need to solve, is this equation here. So that's the last step. So this is a lot of steps so far. We took our homogeneous solution and relaxed that these are constants into functions. We took all of those derivatives, making this assumption here to make our lives easy, and then we plugged that into our inhomogeneous equation. We find that some stuff cancels, and this is the last equation left. So now we have to satisfy this. So essentially, this is a condition that has to be true, and this is a condition that has to be true. So these are the only two conditions on my u function, and this is enough information to uniquely solve for u1 and u2. That's kind of where this came from. Now we're going to use this information. Whew, okay. Well, goodness gracious, let's get at it. So I'm going to use this equation, and I'm going to say u1 dot e to the minus t plus u2 dot e to the minus 2t equals 0. That's one condition. And that's going to tell me that u2, so like move u1 over, this essentially implies that u2 dot equals minus u1 dot e to the positive t. You can convince yourself that if I literally took this and plugged it in for u2, I would get, e to the minus 2t times e to the t is e to the minus t, and I would get a minus u1 dot, and so this term and this term would cancel for this u2. So this actually was not only convenient here, but it gave me information about how these two are related that I'm now going to use. Okay, so that's one condition. Let's call this condition 1, and let's call this condition 2. So condition 1 gave me that information, and now condition 2 is going to give me the information that, how do I want to do this? I'm going to say this is minus u1 dot e to the minus t minus 2u2 dot e to the minus 2t equals e to the minus 3t. That's this condition. And that's going to imply, I'm basically going to plug in my expression here for u2 as a function of u1. I'm going to plug that in here. And now I'm going to get something that's only a function of u1. Okay, and maybe I'll do it over here so I don't feel cramped. And so now I'm going to get an expression just in terms of u1 by plugging this in here. And that's going to be u1 dot times minus e to the minus t plus 2 e to the, oh my goodness, e to the t times this is e to the minus t plus 2 e to the minus t. All of that equals e to the minus 3t. Like, you can slow down or pause and just convince yourself that if you plug this in for u2 dot, this is what you get. And so now things are actually looking pretty easy. It got hairy for a while. Now it's getting easier. Now we have u1 dot times, these add up to just a plus e to the minus t, e to the minus t equals e to the minus 3t. So of course I can multiply both sides by e to the plus t. And that gives me u1 dot equals e to the minus 2t. Good. Which means that there's a lot of implies here. There's a lot of steps on steps on steps. This implies that u1 of t equals like minus 1/2 e to the minus 2t plus a constant. Okay, this is just, I just integrated this expression. I literally integrated both sides of this to get u1 of t equals negative 1/2 e to the minus 2t plus a constant, an integration constant. And again, because we use this condition, this is guaranteed to satisfy this and this. It also satisfies our forcing term here. So that's for u1. I have to do the same thing for u2. Maybe I'll do this in orange. And so similarly, you know, u2 dot equals minus u1 dot e to the plus t. So that equals u1 dot was e to the minus 2t. So this is going to be minus e to the minus t, which implies that u2 of t equals e to the minus t plus another constant, constant 2. Okay? And so now we have u1 and u2. And all we have to do, the last step, is we just literally plug them into this expression, and we're done. So what color haven't I used recently? I've used all of my colors. Maybe I'll just do pink. So I literally take u1 and u2, and I plug them into this expression here, and we're done. So x of t equals okay, this equals minus 1/2 e to the minus 2t plus a constant 1 times e to the minus t plus u2, which is e to the minus t plus another constant, constant 2, e to the minus 2t. And I'm going to multiply this all out, and we're going to find that this equals, of course, e to the minus 2t times e to the minus t is e to the minus 3t. So I have minus 1/2 e to the minus 3t plus my constant e to the minus t. And then this one, e to the minus t times e to the minus 2t is also e to the minus 3. So that's plus another e to the minus 3t plus my constant e to the minus 2t. And then just grouping and collecting my terms, I get x of t equals, what is this? 1 minus 1/2 is just 1/2, so that's 1/2 e to the minus 3t plus a constant e to the minus t plus another constant e to the minus 2t. And that's the solution of my forced differential equation. And of course, you would find these constants k1 and k2 by taking this expression and evaluating it at 0, and taking its derivative and evaluating it at 0, and then solving for the k1 and k2 that make these initial conditions work. So this was a lot more work than the method of undetermined coefficients. It was a lot messier because we're taking all these like chain rules of functions. So it's kind of, we're integrating these u1 dots and u2 dots, and we're making these assumptions. So there's a lot of steps in this, but this is also much more general. This f of t could be almost anything. It doesn't just have to be e to the exponentials and sines and cosines. This could be a really nasty function. All of this is still going to work. So maybe I'll just do one really, really quick recap. The idea of variation of parameters is that you take your homogeneous solution with no forcing here, you relax your constants into functions of time. That's easy. We have the power to do that. And then we're going to solve for these functions that satisfy our inhomogeneous solution. So we go through all of the math and the rigmarole of computing the first derivative and the second derivative. But to make sure that this doesn't get even more heinous in the second derivative, here we set this term equal to 0, and we'll use that later. It turns out this is not just convenient to save ourselves board space, it's also convenient because we need another condition out later. So we plugged this in, we computed the derivative, we made this assumption to make our derivative simple, then we computed the second derivative. We take all of this information now in terms of our homogeneous solution and these undetermined kind of function u1 and u2. We plug that into our ODE, we get all of these terms. But we find that when we collect large amounts of those terms add up to equal 0. And this is generically going to be true, again, because e to the minus t and e to the minus 2t were solutions of our base homogeneous solution. So these go to 0. And now we get a relatively simple differential equation in terms of u1 and u2 and our forcing term e to the minus 3t. So at this point, we're like 80% of the way there. Now what we do is we take our first condition and our second condition that have to be true for u1 and u2 dot, and we just go through the motions of solving for u2 and for u1. So you can first solve for u2 as a function of u1 in condition 1, plug that into condition 2 and get an expression just for u1 in terms of your forcing. You can solve for that u1 of t by integration, and you can solve for u2 of t by integration. And when you plug those in, what you'll find is that specifically these terms here end up being what contribute to your particular solution. So this term here and here ends up, this one and this one, those add up to give you your particular solution xp here, and you still have your homogeneous solution. So this perfectly matches and tracks what you would get by solving for undetermined coefficients, but this procedure is going to be a lot more general for a lot broader class of forced differential equations. Okay, I hope that made sense. That was a fair amount of math, but none of it was super difficult. This is all stuff you should be, pretty expert at doing now. It's just a few steps to keep track of. But hopefully you can kind of remember the major steps here of, solve for homogeneous, relax those into functions. Whenever things get nasty, try to set them equal to 0 as a condition, and then keep going through the math. All right, thank you.